put on the recording. So welcome back, everybody. And the topic this week is to try to wrap up the full configuration interaction theory, which is, you can think of this if you can diagonalize exactly, it is the many-body method of choice. So I'm going to remind you of some of the things which we did last week. And then we are going to start with the Hartree-Fock theory, which is our first approximation to a many-body method like a full configuration interaction theory. So you can think of now, if you can diagonalize, set up a Hamiltonian matrix in a basis, and this is the basis you think represents the physical degrees of freedom which are relevant, then if you can diagonalize, you have solved the problem, because you would have all the eigenpairs, eigenvectors and eigenvalues. However, the problem is that our basis explodes quickly. And that means that we will have to make truncations. And even if we can set up a Hamiltonian matrix, and as we have been discussing, to calculate the different matrix elements is something which we can do with, for instance, the Condon-Slater rule. We know what these matrix elements end up being like. But even if we can set up this matrix may have such dimensionalities that it's going to be beyond what we can diagonalize on high-performance computing facilities, the existing ones. And that means that we need to make approximations. And Hartree-Fock theory is one of these approximations. And you can view this as a kind of kitchen item in many-body physics, because it provides normally a better single particle basis and a better ansatz for the ground state energy. So we are going to link full configuration interaction theory with what Hartree-Fock actually means. And then we're going to derive the Hartree-Fock equations using variational calculus, which is one of the standard ways by which this has been done. But we can actually find a very nice link with the full configuration interaction theory. So let's go back immediately to the whiteboard and try to remind ourselves of many of the things which we did last time. And I'm going to repeat some of the things. And I also wanted to link that with some examples, like the Lipkin model or the pairing model, so that you can gain some intuition about what is going on. Okay, so let me just bring this up and switch to the whiteboard. But one of the things which we did was to redefine the basis of Slater determinants. Now, this kind of expansion is something you can do for any state, but we are often interested in the ground state first. So one of the things which we are going to look at now is the calculation of the ground state energies by doing this through full configuration interaction theory, and then afterwards we do Hartree-Fock theory. But keep in mind that everything we're going to do here is something you can apply to other states as well. So one of the things which we did was simply to assume that the exact eigenstate is something which we can expand in terms of a set of particle-hole states. And then we have an overlap coefficient, CH of T, multiplied with this basis of Slater determinants. Now, the operator H0, which is a part of the Hamiltonian, has this basis HP as an eigenbasis. So we will just call this eigenvalue HP of phi HP. And this is a basis of Slater determinants. So these are by themselves many-body states. These coefficients, which we have, CHP, they obviously represent different types of particle hole excitations. So they represent the overlap between this chosen ground state, the overlap between psi 0 and the states phi h of p. So the states are just a set of Slater determinants which we can set up, and we know the basis states for the Slater determinants. Now, the state psi 0 is an eigenstate. We are assuming that that's an eigenstate of the Hamiltonian H. And psi 0 is then the eigen state for the ground state. Now, the expansion which we set up then in terms of the Slater determinants is something which allows us to calculate the matrix elements exactly, and with a given basis. So what we ended up with then is the optimization or minimization problem, where this ground state energy now is going to obviously be equal or less than the minimum in terms of this basis of coefficients, which now define the eigenvectors. And this contains now a sum over H and P, all these possible states, and H prime and P prime. And then I have the coefficient CHP, complex conjugate, CH prime, P prime. And then I have the states here, and I need a little bit more space. So let me just delete this one and be a little bit less greedy with space here so that I can squeeze everything into one line. So this is the minimization which we are dealing with respect to these coefficients CHP. And this is what we derived last time. So we have a pH and pH prime. We have the coefficients CH complex conjugate, CH prime of P prime. And then we have these quantities which we ended up calling matrix elements, essentially because we are going to rewrite the solution of the Schrödinger equation as an eigenvalue problem. And then it's pretty common in the literature to call this for matrix elements. So this is given by phi of H prime of P prime. And this is divided by the norm. So we would then have a P of H. And in principle, we are assuming that these states are orthogonal to each other. So this reduces normally to a single sum. But now we are just going to leave it as a double sum here, P prime. And then we would have then the states. So this would be the overlap between phi of HP and phi of H prime P. And this just reduces to the sum over the squared coefficient CHP, because we have assumed that this is an O and B basis. So that means that the quadruple sum reduces to a double sum over P and H. And this leads to the standard problem, where we simply end up with a type of problem where we have to find the determinant and the roots of the characteristic polynomial minus this E0 times the matrix I. Or rather, instead of just writing this as an E0, we can write this as just a general eigenvalue. Because this is when we solve this problem here, we are finding all the eigenvalues. So this is not limited to H0. And then when we reorganized everything, when we look at these particle hole excitations, what we had then, when we look at this pH and CHP multiplied with phi HP, when we spelled it out, then this is nothing but a sum over CH, and then we have phi 0, which is the ground state ansatz, plus, and then we had a sum over one particle, one hole states. And this contains coefficients which now run over the single particle states. So if you think back to this one, this is nothing but an A dagger, AI, acting on the reference vacuum state. So this is something which we ended up labeling as a one particle, one hole state. Then we have in principle, we have up to n particle, n hole excitations. So this sum continues, and then we would have a sum which runs over A, B, these are particle states, and I, J, these are states below the Fermi level. We have this overlap coefficient, and then we have a new Slater determinant, which would be an AB, AJ, AI, acting on phi 0, where this one is nothing but this state, which we have used a shorthand for, which goes like phi of A, B, and IJ. And this continues all the way to n particle, n hole excitations. So the state which you see here, or the states, which is more correct, these correspond to what we call the two particle, two hole types of excitations. So that means that we can actually rewrite the whole wave function in terms of this new reordering. So we have, in principle, we have an infinity of excitation because we have an infinity of single particle states, but we will always truncate and then produce an effective Hilbert space. And how we truncate this is something which we often don't have a clear recipe for. So what people often do is that they try to augment the size of your effective Hilbert space, and if your energy of the lowest lying states seem to converge as a function of the increasing space, you would then stop. And obviously the connection with experiment plays a very important role. Now, this is a little bit a repetition of what we did last week. Now, we end up with a set of matrix elements which we can calculate, and we have explicit expressions for these matrix elements. So the matrix elements which we end up calculating are matrix elements of this type. And these are elements which we can find analytical expressions for, and then we can look up in a table, or we can calculate them, the relevant integrals. But keep in mind now that these are many-body states. But then when we set in the explicit expressions for the specific states, we end up with matrix elements which are defined in terms of single particle states. And the reason for that is that we have built up this basis in terms of single particle states which define a Slater determinant. So this is something which allows us to actually have a calculational recipe which is handy and convenient if a single particle picture is meaningful. So let me quickly remind you of some of these other technicalities, because what we end up with having to deal with are matrix elements of the type like this, phi 0, the ground state, and then we have the Hamiltonian acting on a one particle, one hole state. So this would be matrix elements which link the ground state with a one particle, one hole block. We would have matrix elements which then link a two particle, two hole excitation. We can have matrix elements which link a one particle, one hole state to a one particle, one hole state. And we calculated these matrix elements, and we are going to reuse them. So we can have matrix elements of this type, which now link a CD here, etc. So these are the matrix elements which then are essential for setting up the Hamiltonian matrix. So to quickly remind you of some other things which we defined last week. So when we now look at the Hamiltonian matrix, which we end up setting up, this matrix can now be thought of as sets of blocks. And the first block is what we call the zero particle, zero hole block. And that contains matrix elements. And since we have assumed that the ground state is non-degenerate, it means that we will have a matrix element of the type phi 0 of H to phi 0. And we have calculated this one, and we call this for the reference energy. So as a small digression here, this is something which we calculated as the reference energy, because this is the energy we would get with a given Slater determinant, which is an ansatz for the ground state. Now that ansatz can be pretty good, which means that the reference energy we get could be close to the total energy of the ground state of a physical system, or it can be far away, which means that the basis we have chosen for that phi 0 may not be the best basis. Then we are going to have a new block, 1 particle, 1 hole, and then we have 2 particle, 2 hole, 3 particle, 3 hole, and this goes up all the way up to n particle, n hole. That's the possible set of excitations which we can make. Then we obviously have the same blocks down here, 2 particle, 2 hole, 3 particle, 3 hole. This should be 3. And this goes all the way down to n particle, n hole. And here we would then have the matrix elements which link the 1 particle, 1 hole with H and phi 0. Here we would have the same matrix elements, except that now we are looking at the emission conjugate. So this would be a phi 0, H with a 1p, 1h state. The next one will be phi 0 with a 2 particle, 2 hole state. Now for the two-body interaction, last week we saw that these matrix elements, since they are linking a state with a state which has more than 2 single particle states which are different, these matrix elements are 0 if you stop at the Hamiltonian at the level of a 2-particle operator. So that means that all these other matrix elements are 0. And here again, we would have the 2 particle, 2 hole, H, phi 0, and then 0, and all these other matrix elements would be 0. In the middle here, we would have a 1 particle, 1 hole of H, or 1 particle, 1 hole block. And here we would have a 2 particle, 2 hole, H, with a 1 particle, 1 hole block. And for the 1 particle, 1 hole case, we would have a matrix element with a 3 particle, 3 hole, which is possibly non-zero, since we have a 2-body operator only. And then the rest will also be all zeros. So when I put a cross here, that means that they have matrix elements which are non-zero. So this would also be non-zero. And here we would have non-zero, non-zero, but this can also link a 4 particle, 4 hole. But then the remaining ones are 0. So a 2 particle, 2 hole can link with a 3 particle, 3 hole and a 4 particle, 4 hole. But then the rest ones will be 0. And this is a matrix then, which is a kind of band diagonal matrix. So you would have something which goes like this with matrix elements which are non-zero. And what you will have then, if you have many n particle, n hole states, is that this matrix will be pretty sparse. So let's look at a simple example, which you are going to meet in the second midterm. And this is something which we call the pairing model. But let's now look at a system which has n equal 8 single particle states. And they actually doubly degenerate. So they have a spin degeneracy. And then we have n equal 4 particles. Now, what we are going to require now is that there is a Hamiltonian which doesn't break pairs. So this is a special instance. You can break pairs, but let's now assume that we just limit ourselves to the following case. So we have these states, which we will label with a p equal to 1, p equal to 2, p equal to 3, and p equal to 4. And the Fermi level is this one. And the ansatz for the ground state could be having two particles here, two fermions with spin 1/2. And since there's a double degeneracy, this means that we can have two particles in every such state P. Okay? So this will be our ansatz for the ground state. And we have defined a Fermi level, which is this dotted line here. Then we can make a new state. And now I'm going to be a little bit sloppy with the drawing. And what I assume now is that I cannot break a pair. So that means that when I do excitations, I can only promote two particles at a time. And I cannot break a pair. There are actually elements of the Hamiltonian which do this. So you can actually project out a part of the Hamiltonian which only promotes pairs. In the Lipkin model, you have seen something similar. You have a part of the Hamiltonian which allows you only to make jumps to a level where you keep a pair of states with opposite spins. So that Lipkin model, which you have had in the exercises, is not so different from what you see here. But if we now assume that we cannot break any pairs, there is a limited set of options or configurations which you can make. So we could call this state for phi 1. And now you see that the way you set up the states is pretty obvious. And you would have this one. And we can label this for a phi 2. And then we can continue with this exercise. So we can now have this state, this pair, which stays as it is. And then we just promote from the bottom this state. And we could call this for phi 3. And then you will see that there is a final state, which would simply be this one with this excitation here. And we could call this for phi 4. And finally, we have a state which looks like this. This is the final possibility when we do the combinatorics here. And the combinatorics now is us having 4 levels and 2 pairs. So if I take 4 levels and 2 pairs, then I get a total number of 6 configurations. And we can call this for phi of 5. And in this particular case, this is a 4-particle 4-hole excitation. This is an instance of a 2-particle 2-hole, a 2-particle 2-hole. This is a 2-particle 2-hole state. This is a 2-particle 2-hole. And the final one, the ground state, is a 0-particle 0-hole state. So this would define the Hamiltonian matrix. So we can then diagonalize the system and find a result for the ground state as a linear combination of these different determinants. So if we go back then, what we will be missing here is actually this 1-particle 1-hole block, because we have, by construction, defined these to be 0. So we have a Hamiltonian which does not allow us to make a 1-particle 1-hole excitation. It only promotes excitations of pairs. And you can actually rewrite your Hamiltonian in such a way. And that's pretty common, in particular in a field like nuclear physics, where pairing correlations play a very important role. So then you can make an ansatz, a model Hamiltonian for a realistic nuclear Hamiltonian, where you only look at the contribution from pairs to the ground state energy. And that functions often as a very good ansatz for many specific nuclei. Now, if we now look at this kind of Hamiltonian matrix here, what we would have then, if we now write down the Hamiltonian matrix, we would then have a block here, which just contains one matrix element. So there will be a phi 0 of AH of phi 0. And then we would have the phi 0 with all these two particle hole elements. So there would be a new element here of phi 0, of h of phi 1. And this would continue up to phi 0 of h of phi 4. That's later determinant we put up. And then we have the final one. So this would be what we called the two-particle two-hole block. So this is phi 0 with the two-particle two-hole states. So we have 4 of them. So that means that that block is a vector with 4 elements. Then we have the final one, which is a phi 0 of h of phi 5. So this would be a 4-particle 4-hole block, which then connects with phi 0. So in this particular case, if you look at the problem which we have, and if I tell you that we are only dealing with an Hamiltonian which acts at most on 2 particles, so it has at most a 2-body operator, what would the value be for this term here? If you go from the ground state to a 4-particle 4-hole excitation. So that means that you're trying to connect this one with this state here. And we have an operator which acts only on 2 particles of the most. So what kind of value would that matrix element get? If you think back to what we put up here. That's exactly 0. And you can see that immediately here, because if you have an operator which only acts on 2 particles at a time, that means that we could connect these 2 here with so the operator could take these 2 and act on these 2, but then I would have this term here where I take the overlap with this term, and that is obviously 0. So if I have a 4-particle 4-hole excitation and a 2-body operator only, that means that this matrix element will be 0. So there will be, if we now set up these blocks here, we will have a phi 1 with h phi 0. There's going to be a phi 2 here with h of phi 0. And this goes all the way down to phi of 5, which is then 0. So we get to phi 4 of h of phi 0, which is non-zero, can be non-zero, and then we get 0. And this would now be the Hamiltonian matrix. So all the other matrix elements, except for these zeros here, will be non-zero, because I can connect a 2-particle 2-hole state with a 4-particle 4-hole state. So the final matrix element, which you would have on the diagonal, would be a phi 5 with h of phi of 5. And on the diagonal, you would have then phi 4 of h of phi 4. And this goes all the way down here with all the diagonal elements. And then we will have blocks of matrix elements which will be non-zero, because we can always connect a 2-particle 2-hole state with a 4-particle 4-hole state. So the only non-zero matrix element will be the one which connects a 0-particle 0-hole state with a 4-particle 4-hole state. So this is an example of a Hamiltonian matrix which you can set up. Then what we need to calculate is obviously these matrix elements. So for this specific case, when we have a 2-particle 2-hole state, so we would have something like this of h of phi ij of AB. And we found that this is equal to the following matrix elements. We have an AB of V. This is what we calculated some time ago. So if we then have these matrix elements, then we know exactly what they look like. So this will be an AB Vij minus AB and Vji. And these are integrals which we can evaluate. Alternatively, we can tabulate them and just keep them in a table. And then when we have these indices, we will simply look up the different elements in a table and fetch the matrix elements. So this is essentially what we end up doing. And we would then need to calculate the matrix elements between 2-particle 2-hole and 4-particle 4-hole states. Let me also remind you that if we go to the more general case, where we also had a phi 0 with a 1-particle 1-hole case, that translates into us having to calculate a matrix elements of this type, which is now a phi of IA. And when we did the calculations, what we found is that this is equal with a normal ordered Hamiltonian with a respect to a vacuum state, that this case here is equal now to a state I. So, sorry, this becomes an A, and then we have an F and I here. So the state phi I of A is actually given by this AI, AA and AI acting on the vacuum state. And this matrix element AF coupling to a state I is given by the integral for the non-interacting part of the Hamiltonian, plus this correction which we get, which we call the mean field correction. And this becomes important when we're looking at Hartree-Fock theory. And this contains now a sum over states below the Fermi level. And then we have an A of J, of V, of I and J anti-symmetrized. So these are again elements which we can look up in a table, and then we can easily evaluate the matrix elements of the Hamiltonian matrix. So that means that these, which you see here, these are many body states. But since we have defined these many body states in terms of a product of single particle states, then we have a formula which relate these matrix elements here to specific integrals which involve single particle states only. Okay. Now we're going to do something a little bit strange. And this is still a part of a repetition from last time. If we now go back to the Hamiltonian matrix, the general one which we have here, if you now look at this specific row here, that specific row is nothing but us taking the state which are being acted upon by H. So this is actually the first column, if you think of that one like this. So we have all these different elements here multiplied with the coefficients. But then from this side, we actually multiply with phi 0. So we are simply taking the Hamiltonian, which is acting on these states. And if we take the full Hamiltonian problem, what we are having is the following: H minus E0, which is the ground state, acting on psi 0. And this is equal to H minus E0. So this is obviously 0, multiplied with the sum over all these particle hole determinants. So we have made this expansion here, and this is equal to 0. Okay? So this is the eigenvalue problem. If you then go back to the Hamiltonian matrix, the way we have rewritten this eigenvalue problem, what you see now is that every row corresponds to you multiplying from the left with a given set of states. So the first row in your Hamiltonian matrix is actually you taking that equation and multiplying with phi 0. Then the second row is us multiplying with a block of one particle, one hole states. And then you continue along this line. So what you have then is that all these different terms here, which you see, they are obviously multiplied with the eigenvectors. And the eigenvectors are given by these components. So the eigenvalue problem, just to remind you of that one, is actually H times C, and that is equal to a generic eigenvalue times C, where C are now these different components. So each eigenvalue has obviously a different set of components. That sound reasonable? So if we take the first row of that Hamiltonian matrix, first row of Hamiltonian matrix, that is actually us multiplying with phi 0 times H minus E0. And this is then multiplied by psi 0. And this has to be equal to 0. Now, what you see here is that you get a set of equations. So what I'm going to do now is to reformulate the eigenvalue problem in something which you will call a highly inefficient problem. But the reason why I'm doing this is that this allows us to make a nice link with approximations. So you can rewrite an eigenvalue problem in the way we are doing now. So what you end up with is a set of nonlinear equations in the unknown coefficients CHP. So when I diagonalize, if you can diagonalize the matrix, you get immediately these coefficients. These are the eigenvectors, which you have here, for a given state. So just to remind you quickly, if you put a CI here, and an EI, and CI here, these EIs could be the eigenstates of the system. And then each case would have its own eigenstate. Now, so if we do that, what we get then is the following. So we get a phi 0 multiplied with H minus E0, and this is now given by a psi 0. This is the first term. Then I have the next term, which is now when we spell everything out, and we actually, this is roughly where we ended last time, so I just wanted to repeat some of these things we did. And then I have a coefficient CIA, which is unknown. And then I have my phi 0 of H minus E0 times phi IA. Then I get additional terms plus, and then I have a sum of ABIJ, CIJ, the unknown coefficients, and then I have phi 0 multiplied with H minus E0. E0 is just a constant. And this contains now phi ij, AB. And this terminates. If I have a two-body operator, as we discussed last time, this terminates at the level of two-particle, two-hole excitations, because the three-particle, three-hole excitations cannot link a determinant, which differs by more than two single-particle states if I have a two-body interaction at most. And then, if we now go back, we know that since E0 is a constant, that disappears from here because this state's orthogonal, and it disappears here as well because this state's orthogonal. So what we have then, when we take this sum, is that we get a phi 0. So we have a phi 0, and then we have H0, which is now the E. So let's put this up like this, minus, and then I just have E0. This is nothing but the reference energy, which we have calculated, E-ref, like that. Then if I look at the next block with the one particle, one hole excitations, this is just going to be given by a sum over AI of CIA. And this contains now the matrix elements or these integrals. So as I said, we will often just call these matrix elements, but in principle, these are just pointing to specific integrals of a given operator. So this is the second term. And then finally, what we have is an AB, IJ, and then we have a CIJ, AB, and then when we calculate the matrix elements, this is what we have of IJ, and this is an anti-symmetry state, and this is equal to 0. And then we reshuffle this and defined what we call the correlation energy. So we had then that delta E is equal to E0 minus E0 ref, which is equal to this very compact expression of CIA of A of F of I plus the final term, which is a sum of AB IJ, CIJ, AB, and then I have AB of V of IJ anti-symmetrized. So if we diagonalize, we know exactly what these CIs are, but this would be an extremely stupid way, as we said last time, to calculate the ground state energy, because when you diagonalize, you get immediately E0. So in this case, what you would do then is just to fetch the eigenvectors, the given components, and perform these sums. Now, the reason why I'm setting this up is that this is going to set up a recipe which is used in other many-body methods. And one of these methods is copper cluster theory. Another method is many-body perturbation theory. And what we are doing now is simply to move on to, so this is the first row. And if somebody gives you these coefficients, you can evaluate the energy. Keep in mind that you can do this for any eigenstate, okay? Now we're just looking at the ground state energy, because the problem which we have is of this type here. If we now go to the next row, and then what we are going to do now is to multiply out the equations which we have. So these coefficients which you see here, we are focusing on the ground state only energy, but now we multiply with a one particle, one whole state. Actually, we have a set of one particle, one whole states, but now we are going to repeat the same exercise which we did here, but we are going to multiply with a one particle, one whole state, and then we're going to take H minus E0, and this is now multiplied with psi 0. And this obviously is also equal to 0, because we have pulled over E0, okay? So let me just write this out before we take a break. Now, this is equal to phi I of A. Now, E0 is a constant, and since we have an orthogonal basis, this is equal to this term here. And we have calculated this matrix element already. We know what that one looks like. So this contains a phi 0. Then we have plus, and then we have a new term, which goes over B and J. So these are the one particle, one whole states. And now I have to multiply phi of IA. And now I need to keep E0, because there can be terms where E0 is involved. So I have a J and B. Then I get my two particle, two whole piece. So that will be a BC and JK. There's going to be a new coefficient, CJK, BC. And then I have a phi of I of A. Now I can take away E0, because what I will have here is a Slater determinant, which differs from the one we have on the brass side. And finally, since I have a two-body interaction only, this equation here stops at the level of excitations of a free particle, free whole state. So it's going to be a coefficient JKL of BCL. No, so BCD, sorry. And then I have a state phi IA of H of phi J K L. So it's a free particle, free hole excitation. So this is a free particle, free hole. Now, what you see now is that you get a set of equations which you could solve if you have an initial guess for the coefficients. And the thing is now, if you take a closer look here, if you look at the coefficients, this coefficient CJB here is now going, when we are going to set up the equations after the break, these coefficients here will be multiplied with E0. Now, E0 contains the coefficients. So that means that you get an equation which is non-linear in the unknown, or set of equations which is non-linear in the coefficients. Now, what we can do now is obviously to continue this till we have taken care of all the possible rows which we have in the Hamiltonian matrix, where the final one would be this one. Now, you can actually solve, this is a way to solve an eigenvalue problem by solving a set of coupled nonlinear equations, where you start with a guess, and then you keep iterating. And the standard way to iterate is to use Newton's method. So Newton's method pops up everywhere, again and again. So this is an extremely inefficient way of calculating these unknown coefficients when you can diagonalize. However, it allows us to link what we are doing with other many-body methods, which are approximations. And this is the main reason for why I bring up this extremely stupid way of solving a problem which you can diagonalize. Okay? But it gives you a little feeling of what is going on with the other methods, because we often want to link, if you can diagonalize exactly, then clearly there's no need to look at other methods. But if you cannot, then it's very useful to actually try to figure out how much do the other approximations give us to what would be the full exact problem if we could diagonalize. So what we did before the break was to start with this kind of clumsy rewriting of the equations in a non-practical way, where we are going to get a set of coupled nonlinear equations in the unknown coefficients. Now, one of the main reasons for why we are doing that is that in general, even if we can set up this Hamiltonian problem to diagonalize, the dimensionality may be so big that we cannot diagonalize. And then we are searching for approximations to the full problem. So the FCI problem, or the full configuration interaction problem, starts with the basic problem which you have here. This is the minimization problem. And we want to find the best possible ansatz for the energy. And here in the CI calculation, or configuration interaction, we optimize these parameters with respect to these parameters. We could optimize with respect to parameters in the wave function. And there are many different ways of doing that. This gives us, when we translate it, it gives us an equation where we have to find the roots of the determinant. That gives us the characteristic polynomial. And this is a standard problem in linear algebra, which many of you have encountered. It means that basically what we are doing then is that this matrix, by a set of iterations, or what we normally call similarity transformations, we are transforming the matrix gradually to a diagonal form, so that we then can read off the eigenvalues. Now, what we started with before the break was simply now to multiply out the rows. And we were focusing mainly on the ground state, but there is nothing which limits you to only look at the ground state, but you can set up a similar set of equations, which you will see now, for all the other states. So if we now focus on the ground state, if you look at the equations which we have, we are getting this equation for the energy, or the difference between the energy we can calculate with the ansatz, which is the reference energy, and the energy we are targeting. So this difference is normally called the correlation energy. You will see in many-body perturbation theory, this is slightly different, because then this E0 ref is not going to include the interaction piece. Here, this includes the interaction, the two-body interaction as well. But these are just slight modifications. So then we started with the second row, where we now pick one particle, one whole state. But in principle, we have many. So if there are 10, you would then have 10 such states you need to multiply with, but the structure is exactly the same. And this set of terms which we get, that terminates when we now are linking a one particle, one whole state with a free particle, free whole state, if we have a two-body interaction only. Now, if we now look at these terms, this is something which we have already calculated. Then let's take a look at this term, and then we may elaborate on this term here, but I just wanted to bring in the kind of complexities which you get when you solve the equations this specific way. So if we now just look at what we had, we know this expression here. So the first term is just equal to I of F of A, which we have calculated. So we know that one, we can look it up. Now, if we then look at the next term which we have, so in the next term, we are going to get the coefficients, and we know we can single out a diagonal term. So that means that I and A are equal to B and J. So we can single out plus, and now we have a term which has a CIA, which is the unknown coefficient. And then I have my phi of IA, and then I have H minus E0, multiplied with phi of IA, plus, and now I have a sum of B different from A, and J different from I. And now I have a C, I have phi IA, and then I have H, but now I cannot have the E0 term because that is a constant, because these two states are different. So what I get then is just this phi of JB, and then I have the unknown coefficient, plus, and now I'm just setting up these additional terms. So I'm just going to focus on the three first terms. So if we now look back to what we had here, we have a term which connects a two particle two hole and a term which connects a three particle three hole. I'm just going to leave them out, just because when you start making these iterations, you need to make some assumptions. Now, one of the things which you can see here when we now calculate these elements, so if we now go back to this phi IA, let's take this term first. This is something which we calculated last week. So this is obviously equal to phi of IA of H, and then we have phi of IA. So this contains a CIA coefficient minus, and then I get a CIA of E0. Now, the terms which you see there are terms which we have calculated, and I'm just going to list them here, and I'm not going to repeat the calculations of these terms, but what we get is the following, and let me find my old notes here. I just need to figure out where I have them. Okay, so when I now plug in things, what we are going to get is the following. So what we get is an I of F of A, and then I have this term which now contains a term which goes like I of F of A, minus I of F. So that's the first element. And this contains an addition, a matrix element of A of J, of V, of I and J, like that, anti-symmetrized. And this is multiplied with this coefficient CIA. And it contains a sum here over the states J. No, wait, no, this is wrong. This is actually wrong what I put up here. Sorry. This is actually wrong. Let me just correct it. I just read off the wrong line here. So it has a matrix element which is plus, I just looked at the wrong line here, AI of V of AI. That's that specific matrix element, anti-symmetrized. Then it has the term B different from A and J different from I. And now I have the coefficients, the unknown coefficients, and I have a phi of IA, of H, of phi, of J, B. So this term here translates into a specific matrix element, which becomes equal to A of J, of V, and B of I, anti-symmetrized. So this is the next term. And then we have the other terms. And this is equal because now I switch EC to CI of A here. So it's it's not a very practical way of writing it, but we have a set of equations which we can start solving with a given guess. But now the thing I want you to notice is that here these coefficients appear as a linear coefficient. But then when you go back to the equation for E0, which we found before the break, then you see now that there is another coefficient here. And this is why we call this a set of nonlinear equations in the unknown coefficients. So the common way to solve this is to solve it iteratively. So you would solve iteratively with a guess. With a guess, which we call CIA0, CIJAB0, etc. And if you do perturbation theory, which is a very common guess, so in many-body perturbation theory, in MBPT, you can actually find an expression for this. So this is something which we are going to show. In perturbation theory, the CIA is actually given by the matrix element F of A divided by the energy difference between particle states and whole states. So in many-body perturbation theory, to second order 2, so this, I have to specify that. So this is something which we will derive a little bit later. Then you can actually set in a guess for these coefficients. You will also find that the coefficient Cij of AB, and we are coming to this a little bit later, is going to be given by this integral of epsilon I plus epsilon j minus epsilon b minus epsilon b. So this is a kind of guess you can start with. So this will be your C0. Then what you would do then is also for this specific guess, you would put Cijk, ABC 0, and all the other ones equal to 0. And then you can go back to these equations set them in, and then when you do that, you will find a new, because then you are going to plug in the equations in here and in here, and then you will iterate again. And the hope then is that when you then iterate again and again, that this expression which you have for the energy here, after some iterations, doesn't change more than a quantity you have decided. So you would calculate the energy, E0, by setting it this ansatz. So when we are going to derive the equation for perturbation theory, many-body perturbation theory to second order, you will then have analytical expression for these equations. So if you can diagonalize, these are the components of the eigenvectors, but we can retrieve this with many-body perturbation theory. We can also retrieve this by solving these equations in an iterative way with a non-linear equation. That gives us copper cluster theory. So copper cluster theory would then mean that if we go back to this equation, which we have here, this Hamiltonian matrix, is that we would put this term to 0, this term to 0, and so this is H minus E0, H minus E0, we would just put them to 0, and then solve iteratively this set of coupled nonlinear equations. This means that we would zero out this block, we would zero out this block, but we would not do the same thing with that one, and we would not do the same thing with that one. So this would lead to a strange type of transformation of the Hamiltonian matrix. But these are methods which will come, but just keep in mind that what you end up doing is approximations to that full problem. So if you think of the diagonalization case as the gold method, if you can do it, then you have the answer. But in general, your basis is going to be too large. So you have to cook up smarter ways of dealing with it. Okay, so the thing which I want to do now, we mentioned a little bit last time about the diagrammatic representation. I'm going to skip this now because I wanted to introduce a little bit the Hartree-Fock recipe. And if we now go back to the Hamiltonian matrix which we had, so let's just bring up Hartree-Fock theory. So this is our first approximation. Our first approximation. Now, if you look at the Hamiltonian problem which we have put up, so we have an H times an eigenvector, which is equal to some energy times the eigenvector. So how do we solve this numerically as an eigenvalue problem? So the standard approach, which you probably have encountered in textbooks on when you took a course on linear algebra, or if you've been taking courses in computational mathematics, numerical mathematics, computational physics, etc., you have probably encountered this kind of standard approach. So the standard approach is to find a transformation of your Hamiltonian. So where you have a U acting on H, and this is normally a unitary matrix of U. If the matrix is a real one, it would be typically an orthogonal matrix. And this is a transformation which then transforms your matrix into a diagonal matrix, where you then would have all the eigenvalues up to a given dimensionality D minus 1. So these transformations have obviously the properties that they obey unitarity or orthogonality. So this will be equal to the identity matrix. And then we know that U, the Hermitian conjugate, is actually equal to the inverse of that matrix. Okay? So if you're dealing with real matrices, then this would just be standard orthogonal matrices. And we know from the first exercises that this is such a transformation acting on the vector C preserves the norm and preserves orthogonality. Okay, so these are very important features. In essence, when you look at all the methods we are dealing with, you can think of they as being methods which are acting on a basis with a unitary matrix. So obviously, if you can solve the problem by just one such transformation, you're basically done. The problem is you cannot do that. Unless you have a 2x2 matrix, you can use Jacobi's method, and it's very easy to find the transformation. But in general, what you end up doing then is a series of such approximations. And in a way, you have to terminate this approximation when you think you're done or when your convergence criteria has been reached. And that means that if all the non-diagonal matrix elements are smaller than a certain number, which we want to be as close to 0 as possible. So what you would have then would be a series of such transformations, u of m minus 1, and this goes down to u of 1. And then you have h, and then you have u of 1, u of 2, up to u of n. And then your matrix is hopefully a diagonal matrix. This is the essence of the diagonalization problem. And now we can use this to actually interpret what happens when we do a specific transformation. So are you all familiar with Jacobi's method for finding the eigenvalues of a matrix? So Jacobi's method, if you think of a 2x2 matrix, is a rotation around an angle. You have another method which is called Householder's method, which is a rotation around a plane. But Jacobi's method, if we now think of this as a 2x2 matrix, that is given by a cosine theta. There is a minus. This depends on whether you rotate clockwise or counterclockwise of cosine theta. So that's the so-called Jacobi transformation. And if you have a 2x2 matrix which you're transforming, the way you zero out the non-diagonal terms. So if I do that, I would have on a 2x2 matrix. So these are now 2x2 matrices. This should now give us a lambda 1 and a lambda 2 here. And you choose the angle theta in cosine and sine so that the diagonal elements are 0. So that the non-diagonal elements are zeroed out. So your original matrix could be something like this. It could be an H11, an H12, and an H21, and an H22. So when you perform this rotation with a U of H of U, this gives you an H11 tilde and an H22 tilde and 0, which are then the eigenvalues, lambda 1 and lambda 2. So if you have studied Jacobi's method, then you've probably seen that the way you would do this is to find an equation which allows you to zero out the non-diagonal elements by choosing an appropriate angle theta in the cosine and sine terms. And this is pretty standard in linear algebra. But as you can see, this is a very inefficient method because when you have a big matrix, it's actually acting on only one if your matrix is symmetric. If this H12 and H21 are the same, you only need to look at one of them. But then it just zeroes out one element at a time. And that's extremely inefficient when you want to solve a large eigenvalue problem. But the basic philosophy is this one. So if we now perform a transformation of the full Hamiltonian matrix, So you can now think of a specific U which leaves out, or which zeroes out, the one particle, one hole term, which links with the ground state ansatz. So that means that we would have a U acting on H, the original one, which we had before the break, which now gives us, if we think in terms of this zero particle, zero hole, one particle, one hole blocks, two particle, two hole, three particle, three hole, etc., up to n particle, n hole, that this is going to give us now is a new element x tilde. But then we have zeros for the one of the non-diagonal elements, but only one of them. Then the one particle, one hole block is different from zero. The two particle, two hole is different from zero. This is by definition zero because we have a two-body interaction only. This will be different from zero. This will be different from zero. So we have this would be the two particle, two hole case. And then we have the three particle, three hole. And the one particle, one hole can actually connect with that. And then we have zeros. So here we would have a two particle, two hole block, which is not necessarily zero. And this would continue along these lines here. And then we have zeros. So it will still be band diagonal, but we have achieved something now, which hopefully gives a connection between the ground state and so this case here, where these matrix elements are small. So that's what we're hoping for. So it means that if we look at this problem here, the hope then here is that the new E0 ref is below, so this is the new one, is below the old E0 ref. So that it is a better approximation to the ground state energy. So keep in mind now that this x tilde, since you have only one element, is not the exact value. It's not the exact eigenenergy because we haven't diagonalized the problem yet. But what we are hoping is that disconnecting the one particle, one hole block, that we're getting close to something which is a better ansatz for the ground state. Now, what this means for us is that if we now look at this block, one particle, one hole to H0, no, phi 0, or vice versa, if we just take the Hermitian conjugate, we know that this one with H, or 1P, 1H, for a given state, when this one is given by phi 0 of H of phi I of A, this specific state, if we single out that one, but this applies to all the states, we know that this matrix element is given by the matrix elements of A, of F, of I, which is nothing but the expectation or the integral over H0 of I plus this sum over J less than F of AJ of V of IJ anti-symmetrized. And we are setting these elements to 0. So what is normally called the standard Hartree-Fock which we are now going to derive. So the standard Hartree-Fock means the following. Well, it's often also called the canonical Hartree-Fock, but I would just call it the standard Hartree-Fock, is that these equations which you see now, A, are going to define the Hartree-Fock single particle energies. The I, the states below the Fermi level, I, are going to define the whole energies or the modified energies. And then we are going to have an I of F of A equal to 0. So that means that what we are going to have now is an operator, which I'm going to call H Hartree-Fock, which acts on a given state P, and that gets the single particle energy. So this operator H Hartree-Fock has now P, this new basis P, as an eigenbasis. Okay. So what we are going to show, so I'm just anticipating some of the results, is that the this H Hartree-Fock here, we are going to show that that is equal to, as an operator, is equal to H0 plus some Hartree-Fock potential. Now, this H0 is the one we are used to. So that contains kinetic energy, which we wrote with a T, plus some external potential. It could be a harmonic oscillator, for instance. And this quantity U Hartree-Fock is now going to be given by, so if I look at this term here, if I take and write it out as an integral of U Hartree-Fock of Q here, this is going to be given by this last term, which we have I less than F, and then we have P of I of V of Q of I. And P and Q can be states above or below the Fermi level. What we are also going to get now is that this new basis defines a new Slater determinant. The new basis, P, defines a new Slater determinant, defines a new reference state as a Slater determinant, if we're looking at fermions only. And that reference state is now going to be given by just one Slater determinant. So that state, this phi 0, which we had before, is now going to be replaced by a phi 0 Hartree-Fock. And the hope is that phi 0 Hartree-Fock, this expectation value here of H of phi 0 Hartree-Fock, this, since this is going to be derived using the variational principle, it's going to be larger or equal to the exact energy. So E0, as it stands here, is the exact ground state energy. However, what we also want is that this phi of HF of H of phi 0 of HF is smaller or equal to the ansatz we started with. Like this. Okay. So the this is basically the hope which we are trying to deal with. And with that, we now need a recipe to find this new basis. And there are actually many recipes for doing that. So how do we find P? Because when we have a recipe for finding P, we will also find this potential which we have defined here. And we are going to show that that potential is actually given by this term here, which again means that this operator, Hartree-Fock here, is the same as the operator which we defined for the one-body operator with respect to a new reference vacuum. So this is normally called the standard Hartree-Fock. Now, there are many ways to find that. So basically, the calculus is based on variational calculus. That's the main recipe. And we use the variational theorem. So the basic approach is variational calculus. And I'm going to remind you of variational calculus. One way to do this is actually to look at the single particle wave functions we have and make a small change in them. So this normally leads to a coordinate space variation. So I'm just giving you the variation. So that means that we have a state which we start with, and this could be one of our states which now depends on x here. And this is now changed into a phi of alpha of x plus some change delta alpha of phi. Now, so delta, not that delta alpha, phi of alpha of x, where this change is a small variation in the single particle state. Now, this leads to a recipe which was very much used before it was wiped out by standard linear algebra approaches. So this leads to a set of coupled integral differential equations. Integral differential equations. I'm not going to cover that because that as a recipe leads to a little bit more tricky numerical approach, and which can also be prone to instabilities. And you will also need, since you're going to have both a differentiation operator, which is the kinetic energy, and you need to calculate the integrals, it's going to be very much dependent on the number of integration points you choose. And it's normally an approach which has been abandoned and has been replaced by the variation of the coefficients. So in the lecture notes, you will find an exposition of one. I'm not going to cover that in the lectures here, but you can look it up in the lecture notes. And that is what has been called the standard traditional approach. But when you vary the coefficients, if you now think of the basis, this is the Hartree-Fock basis. So we can expand this one in terms of another basis, which could be our original basis, which we use for the reference vacuum state. So we need to calculate these overlap coefficients. And then we have the original basis, lambda. And we are going to vary these coefficients. And when we do that, we will get a set of eigenvalue problems, which we will solve iteratively in order to update the coefficients. So this again becomes a iterative procedure where you will have a set of linear equations for the unknown coefficients. So we are obviously in a situation where we don't know these ones and we don't know that one. So the way you typically solve this type of problem is to start with a guess and then you iterate. So this is what we will derive tomorrow. Then there is a very nice approach, which I really like, because that allows us to make an analysis of the stability of the Hartree-Fock equation. And that is to perform the variation in second quantization. So this means that this is a slightly different way. So this is to derive the Hartree-Fock in second quantization. And I will try to explain to you what that approach entails. And it gives us a very elegant way of finding out what are the stability conditions on the Hartree-Fock equations, which we will start discussing a little bit more in detail tomorrow and also next week. But the kind of standard approach in Hartree-Fock theory, which basically everybody does, is this number 2 here. Because even if you have a basis of, let's say, 10,000 single particle states, the Hartree-Fock equations entail then just a diagonalization of a 10,000 times 10,000 matrix, which can be done. So that means that you would have 10,000 coefficient, 10,000 basis functions lambda, which you would perform the expansions upon. If you have chosen the basis in a careful way, you may actually only need some few expansion coefficients. Okay, so this is essentially what we will do tomorrow. So part 1 is actually in the lecture notes, but I will start tomorrow by reminding you a little bit about variational calculus and what that entails. And then what we are going to do next is to reuse things we had in the first exercises, the first week, and we're going to vary the coefficient Cp lambda. And that will give us an eigenvalue problem, which we solve iteratively, starting with a guess for the coefficients.